Now, without further ado, let's hear from our next speaker, Paul Chang. Mr. Chang worked as an international oil and gas consultant from Algiers to the US. He retired from 2016 from Saudi Aramco. He has an extensive background working internationally for major exploration projects on and offshore, and he also received 2 patents from USPTO and advanced materials, plus additional patents pending. On his off time, Paul likes to garden and cruise Chesapeake Bay to Pecosby in the 1985 Hatteras Classic. Hi, Paul, how are you?
Fine, thank you. And thank you for this wonderful opportunity, Michael.
Thank you. The screen is yours, Paul.
Okay, I think Dallas would love to chat with you more because I think we might dovetail into your area.
That's why I put y'all in this this program, this block, specifically so y'all could chat.
Would love to do that, Paul.
Okay, so let me get going on the presentation. The first part might be history, just to lay some groundwork so that everybody's on the same page, and it's really for my benefit too. I know you guys are miles ahead of me, but just to build a case, and then we'll get talking about the what I like to offer, and then something realistic of making money to keep this thing running. This is technology that's started with a pipeline and the nuclear. When I first saw this in 2012, I thought, you know, there's a need for it without really understanding how or what's done to it. But so pipeline and nuclear, they want heavy, thick, and powerful. So now to do a 180, to go to space, the thinking has to turn the other way. Miniature, light, small. And so I proposed a demo weld unit to ESA and some folks at NASA to have a demo weld unit on ISS, and it can fit inside the Bishop. So it can be done. It's old style technology. It's not cool. It's not, you know, code. It's not 5G. It's not renewable, but it is basic fundamental science. So I think it has the, in reference to some of the earlier discussions about the 11-kilometer wide structure that's being contemplated by the Chinese taikonauts, or I've been thinking too small. The biggest structure I've been thinking to date is 1 kilometer. I gotta go bigger. We can weld in space. Yes, ultra safe. Astronauts can weld without being welders, and that's critical. Next. If I may just read some history by NASA. This a review of welding in space and related technologies, NASA 2020. Deployment of welding and additive manufacturing technologies in the space environment has the potential to revolutionize how orbiting platforms are designed, manufactured, and assembled. These technologies offer the option for repair of sustained damage to habitat structures on space missions, as astronauts will be able to manufacture new parts and weld cracks. An added benefit is that required repairs can be achieved more economically, as new parts need not be shipped from Earth. With further maturation of in-space welding capabilities, astronauts can operate under given standards and weld damaged structures rather than rely on cargo resupply. Next. And this is from the European Space Agency, November 2019. I'll just read a little bit. Welding and joining, and the last phrase, will enhance reliability and reduce the risk of the often observed underperformance and failures. So they're looking for solutions also. Next, please. So just briefly in history, the Russians were the first to weld in space. 1969, Soyuz 6 in the Vulcan welding unit. NASA followed in 1972 with the Electron Beam. And since then, it all came to a stop. And nothing's been done for the last 45 plus years. My belief is it was never pursued because NASA and Russia deemed welding in space too dangerous and they could not scale. Next, please. So I think it's the aspiration of mankind to travel amongst the stars. And some of these structures on the right are the winning designs given by NASA. But before we do that, next, please. We need support structures, as Dallas mentioned, and a few other folks have mentioned earlier. We need a Pony Express, an outpost, charging stations, just like in the old frontier days. Next, please. Now, if we agree on the assumption that we need to scale, we need to build the Pony Express, the question is, do we do the individual supply flights where we take off, carry the load, land, and leave the infrastructure on Mars or on the moon? Or we load from orbiting stations by lift or by flight? Remember the Jetsons, this is what I call the commuter bus that never lands. So we load from orbit, travel the distance, unload, come back. That's it. It never lands, it never touches Earth or the moon or the Mars. Next, please. So if we agree we need space stations and infrastructure on Mars and beyond, just like the movies. My first sci-fi movie was HAL, Space Odyssey, 1969, I think. So how do we assemble large structures in space and on Mars or the moon? Today's options might be prefabricated parts that clip, bolt, glue, or Velcro in place, amongst a few other stuff. Next, please. But the support structures, whatever we build, must be robust. Permanent space stations must withstand vibrations and the odd impacts, because if that bus goes between Earth, Moon, and Mars, one of these times something might happen, it'll bump into something. And how do you repair that? And the structures on Mars must withstand windstorms. If I believe Matt Damon and The Martian, the windstorms on Mars can be severe. But much more to learn about that. Next, please. So there are different options to weld. Welded structures offer strength and rigidity. It can be repaired on site without waiting for replacement parts. This is one of the most efficient, the fastest welding. One of the options is K-TIG by Australia. Welding in vacuum and zero gravity offers challenges, but there are options. Techniques are fast, works for thick and dissimilar material. But this technique doesn't work in zero G. It works in in vacuum, but not zero G, because when they melt the metal, the splatter is cannot be accepted. Next, please. So friction stir welding and electron beam are the current accepted options. The picture on the right, as I'm sure you folks know all about this much more than I do, is electron beam proposed and researched by NASA through a company in I think it's in Florida. The electron beam on an umbilical cord. Electron beam is great, but there's other issues with that. Next, please. Now, friction stir welding, this is aluminum. This is the cross section with today's technology. The process is 1 millimeter at a time. There is a beginning and there's an end, and we need to inspect afterwards. Next, please. So, to get to the heart of this presentation, what if there is a weld that is truly automated, autogenous, fine grain base to base, in compression, low to no residual stress? That's an assumption for now, being tested and verified by an institution. It resists embrittlement, and there's no fusion line. It is ultra safe and zero toxic fume. For pipeline and confined space, the toxic fume is becoming a very real issue for Earth applications. And the embrittlement is not so important for space because we don't have hydrogen embrittlement out. We have radiation, but not embrittlement. Next, please. So, what if we have an alternative that delivers this quality? For the non-welding folks, this is one of the best welds on Earth right now. No BS, on the level. None of our overseas competitors have this ability or the concept to make this quality. Next, please. I'd like to talk about solid state induction. There are three variables. The quality and the integrity is documented in real time at the job site, in orbit, and at HQ, like in Houston or on Mars or on the moon. There's no interpretations required, strictly by the numbers. The majority of the power is induction heat. It supplies over 95% of the required power to join metal. Shear and forging force comprise less than 5% of the total required energy input. That is significant. So on the comment on the left, this technique welds with technicians, not welders. So astronauts can weld in space without being welders because there's no human input. Once you set the parameters, you're done. Pardon me. Once the parameters are set, there's no further action. It is one shot, less than 1 minute per weld, regardless of size or thickness, and is repeatable. And for tubulars, there's no root weld. For space, is not important because we have no liquid on the inside to go through. For the OD and ID, they're identical, and we can regulate the profile to be flat. Next, please. These are samples of the welds done today. As is, please note the OD and the ID for the folks in manufacturing and the corrosion specialists. There's no preheat, there's no post-weld heat treatment. As is, the minute it's done, boom, that's it. What you see is what you get. Next, please. So these are the Xrays that I did in 2012 or 13. As is, from the X-ray people, 7 out of 7, no porosity, no inclusions, no slags, perfect, flawless. Next, please. And this is a cross section on just a regular grade X65 line pipe, nothing spectacular about the metallurgy, but this is a cross section. There's no fusion line in the middle. There's no heat affected zone. There's heat transition zone, no question, but there's no heat affected zone. And the 3 samples on the right are from Bruce Nuclear Power, given to me with permission to publish. Next, please. So to go back to the basics of what this is all about, recall in high school, we're told when you weld, keep both parts absolutely stationary, don't move it, and then put your stick in there and fill the gap. And afterwards, don't touch it, let it cool. But the problem there is we have 2 heat affected zones on either side of the weld. And that's a weakness. We'll come back more to that later on. So the brilliance of this technique is this inventor said, one part keep it locked tight shut. Put a heating paddle between the work faces. Traditional thinking up to today mostly has been we heat the girth around on the outside. But the brilliance of this invention is you heat between the work faces, up to a certain temperature, pull the heating paddle out, push the other part in and rotate, or rotate and push the other part in. By movement, you break the crystalline structure. That's why the crystals are so fine. And you relieve all the pressure. For pipeline and the hydrogen embrittlement that's coming up for the European and the US market, that is a critical, significant difference. So next, please. So at the end result, when you take the heating paddle out, you move it in, you rotate. And it's just a little bit of a rotation. You don't need a whole lot. And it's not friction, because friction, you go by not, a million miles an hour, dangerous, but there's just slight movement. Next, please. So for the metallurgist, this is one of the finer details of the crystalline structure. To most of us, it doesn't mean that much, but it is significant. The crystalline structure on the left is the base metal. The bottom left is the base metal into the heat transition zone. And the middle picture is the middle of the heat transition zone. But the most important is the bottom right. It is the beginning of the heat transition into the recrystallized zone. There is not that much difference. The crystals are fine grained. I have more on that, but if you're interested, we can get more into that. Next, please. Fundamentally, this is the difference between what was invented and the fuse ring technique. The old method, as mentioned, one side is stationary, put a heating paddle between the work faces, pull it out, push the other part in and rotate. The fuse ring concept and the is what happens when you come to the last joint at an expansion joint or a valve for pipeline. Those are big stuff. You cannot move either end. Or in a nuclear reactor where the feeder tube comes in and the manifold is this side, you cannot rotate either side. What do? My proposal was you put a coupler in between the two sides, heat both faces, pull the heating paddles out, rotate the coupler and push. The two ends, one of them might move laterally, but they'll never twist. So you rotate the coupler instead and push the one end in that can move laterally. And the USPTO says, yes, son, we agree. And they gave me a couple of numbers, granted. Next, please. With this technique, we can work for three-dimensional structures. Tubular pieces can be assembled in 3 dimensions for space assembly using fuse ring technique. Fuse ring can be used to complete circular rings for, say, space station. We can assemble very large structures using this technique. Solid state fusion and fuse ring technique allows welded construction on the moon, Mars, and beyond. Next, please. So fuse ring joints, I've moved beyond that. Further IPs have resolved the problem. The puzzle has been resolved. We can use this technique to join flat, curved, and tubular geometry, regardless of size or thickness. So the applications are pipeline, refinery, nuclear refurbishment, shipbuilding, pharmaceutical, and food. Pharma and food is important because we offer a smooth ID, and that manufacturing sector needs and demands a flawless ID because they cannot have any germs or any bacteria buildup. And we can weld shut spent fuel container lids next to fuel pellets safely because the technique is automated and it resists embrittlement on the inside and the outside against the hydrogen embrittlement. The third one, we can join 3, 4, 5-inch thick hull with no flaw. Submarines can dive deeper with certainty because we have no heat-affected zone. And it can join irradiated material because it's automated, it's one shot, and it's solid state. No human ever needs to be near the process. For dissimilar material, intermediary between very dissimilar materials, the IPs are published for the automotive, for nuclear, different parts. But the last part, the most recent IP filing is rail. The hardness of this technique is much more homogeneous and it takes less energy. Next, please. So to make some money to pay for all the IPs and the presentations, rail is the lowest hanging fruit. They have pain. Fuse ring is the solution. And as a comparison, today's technology on the left is linear friction, sponsored by the government, because they're looking for better methods to join rail. And I'll explain that in a little bit. The top right picture is flash butt. It is the accepted technology for the last 50 years, because that's the best we can do. We accept it and we live by it. We live with it and we work around it. Linear friction is the new exploration area. The heat penetration is less, but the forging force is huge. And so far, they have not been able to overcome that forging force, so it has not been able to be portable. The fuse ring offer, our heat penetration is in millimeters, singular digits, millimeters. The remaining forces, the shear and the forging, are less than 5%. It's insignificant. So it can be portable and the entire process can be electric. Next, please. This is the picture on the left is a picture of rail with two heat affected zone today. And if you look at the picture on the right, the two dips are the heat affected zone and the softness that goes with a traditional heat affected zone flash butt welding. They go about almost an inch either side of the weld face. We accept it around the world. In the global economy, the global rail industry accepts these two dips because it's been fine all these years. But now rail load, speed, and intensity is increasing. Every load is heavier, faster, and they're coming in faster in between the travel. So repair and maintenance is getting to be a significant issue. If I may just point out, a smaller picture on the bottom left is a hardness mapping of the fuse ring solid state technique. Hardness mapping is much, much more homogeneous. We don't have this particular dip issue. Next, please. So just in brief summary, fuse ring is in discussion with US and European companies to demo, mature, and scale this technique. The number one, as mentioned, the lowest hanging fruit is rail, because they have pain, I have solution. Second is a pipeline for hydrogen. Hydrogen embrittlement is a big, big issue around the world. And as far as I know, the Europeans are quite a bit ahead of us on the renewable pipeline infrastructure, because they're studying a lot. And I've attended some of them, and it's a serious concern. And the last one is a proposal to send a demo weld unit onto ISS for aluminum. We've done steel and titanium. Technique, quality, perfect, flawless, same of what you see. But aluminum, I don't believe anyone has tried this on Earth yet. So I would like to propose a miniature that fits inside Bishop as mentioned, and probably something in a few kilowatts power. And the size will be maybe 1 inch OD by 1/8 of an inch wall thickness. It can be done. I've been asked, can we do more with this demo? But I said, let's just do one thing right once. Make it historic. And that'll be it. Come back and do another one, but we can do more after that. Because if I screw up the first demo, if the first weld in 50 years fails, then we might not try welding again for the next 50 years. So make it significant, make it work, make it simple, and then we can plan further, bigger, more complex demos. So for the last two slides, next please. It's really, I don't know who's in the audience. So really just to highlight that for heavy industry, Heat affected zone is a big issue. We monitor, we inspect, and I'll be presenting to ASME Robotics in about 2.5 weeks on this very issue. We inspect and re-inspect because we're not certain, and we need to be 100%, 110% certain. And the heat affected zone, the breakage is universal around the world because this is the way it's done, and this is the way they've accepted it. But I'm saying there's a better way. And this is a study by Enbridge. Next, please. And the last slide is a report by Exxon. I think we have an Exxon R&D person here in the audience. I'm not sure. But anyways, using your studies, the girth weld problem is undermatched. The line pipe, the heat affected zone, the softening, as with the rail, are critical issues. So we offer a better technique, a better way to do things, but we are up against very well-established traditional industries that has a built-in interest to keep things the way they are. But that's reality, and that's what we're working with. Michael, that's all I got. Thank you for your time.
Thank you. Thank you, Paul. Really appreciate that. You know, most folks on this call, most folks in the industry do not have your kind of industrial background, right? So in a way, we're, you know, part of what we're trying to do with this event is intentionally to reach out to folks that are not typically in our sphere and find out what innovations they've got, right? I don't know if you were in the chat earlier, but there was somebody who was asking about heat dissipation in space. For these enormous space-based solar power systems, figuring out how to get the heat off of those systems is really complicated. There is going to be some sort of radiative environment. Somehow you're going to have to hook these radiators together, right? Ultimately, you're not going to build what you want to build in space without figuring out the basic requirements of welding. So thank you for that.
You bet. I'm learning too, because I spoke with Ajith, I think I can mention his name, with Nano, and I learned a lot from him. Because when you have an experiment in space, I didn't realize the ISS has power limitations. I always thought, you know, all those solar panels got tons of power, but you don't.
No.
And I don't want to be the first to black out the station. So
that would be bad.
That will go into the history books. Paul Chang, blackouts, ISS, bad boy.
Right. All right, we're gonna move back to Dallas. I really appreciate that you were here. Please stick around.